Hello, and welcome to Exploring Global Problems, a podcast where we talk to academics from Swansea University whose groundbreaking research is tackling global challenges, from health innovation to sustainable futures and the environment, from digital technologies to clean energy. My name is Sam Blaxland, and today I'm joined by Dr. Ian Mabbett, Associate Professor of Chemistry at Swansea University. His research explores clean energy generation, storage, and its use. In particular, he is focused on low-cost printable solar energy and creating buildings that act as energy hubs. Ian, welcome to Exploring Global Problems. It's good to see you.
Thank you very much. Good to be here.
To begin with, could you just give us an overview of your research and its associated global challenges?
Sure. So a lot of what we'll talk about today is around a project called Sunrise. So Sunrise is funded through the Global Challenges Research Fund, and this explores how we can revolutionize solar energy in India, but in particular through using buildings that generate, store, and use renewable energy. The buildings themselves are the end of the story in a sense, but in the pipeline up to that, we've got a lot of researchers across institutions in the UK and in India who are developing fundamental science, so solar cells that can be printed in the same way that we would make a t-shirt, for example, to bring down the cost of production and make that available more readily to people across India.
We could definitely unpack all of that, and that's a huge topic. But just to go right back to the fundamentals and about renewable energy, why do certain countries, particularly with growing populations, why is it sensible or practical for them to invest in clean energy, renewable energy?
I think one of the big issues, if we take India as an example, there's a big effort to get 300 million people who currently don't have access to power, 24/7 reliable access. Now, one of the issues with that is that if we were to do that by burning fossil fuels, we would increase the demand on fossil fuels. I mean, we have to bear in mind 300 million people is substantially larger than the entire population of the UK. So if they started to burn fossil fuels, the CO2 impact would be immense. So what we have in places across the global south is an opportunity to leapfrog fossil fuel production so that we can move into clean energy futures, which lower the impact while still giving people an increased quality of life and also productivity to whatever it is that they do.
Yeah, because when we talk about, for example, this country's carbon emissions, it pales into complete insignificance, doesn't it, when compared to what people often cite, India and China. So this is part of your work.
It certainly can, yeah, and that's true. So again, it's just comparing the population. So 1.2 billion people in India, 65 million people in the UK.
And again, going right back down to the fundamentals, how would you define renewable energy? What is it?
Well, renewable energy is ultimately energy that comes from a source which is sustainable. So ultimately, we often cite the fact that most energy comes from the sun, one way or another. It can be locked up in sources such as fossil fuels or dead dinosaurs, as I like to call them, and we can release that energy by burning them. But once we've done that, it takes millions of years to restock that energy. If you take things like solar power, wind, these are using sources that are available to us every day. And we know that every day enough solar energy falls on the sun to power us for 27 years. But we just have to get a bit smarter at how we use that. So, as I say, ultimately, renewable energy is just a form which we can use day in, day out without having to worry that we're going to run out of reserves. And a bonus to that, when we talk about clean renewable energy, is that we're attempting not to release greenhouse gases into the atmosphere, which give us air quality issues as well.
So there's obviously lots of advantages to using these renewable energy sources. What are the drawbacks and disadvantages? Some of them are a bit unreliable, aren't they?
I mean, that can be an issue. So, of course, solar energy works when the sun shines, and wind energy works when the wind blows. So we have to think about how we store energy. And that's probably one of the key enablers. And you see a lot of effort in research environments at the moment focusing on storage. I often tell people that there are lots of ways, there's always been an energy storage issue, The difference is that if you're storing with fossil fuels, you tend to store it before you convert to electricity. It's a shift in mindset to think about how we store electricity once it's been converted. To explain that a little bit more, if you've got a petrol tank or a gas tank or a gas bottle or a coal store, you are storing energy. You're just storing it before conversion. It's more challenging to store it once it's been converted.
And the conversion bit, for example, with gas or coal or oil would be when you burn it there and there, yeah?
Burning it, yeah.
And something like solar and wind, obviously the wind is blowing or the sun is being beamed down. Is there one of these sources that's particularly hard to store? Is it solar energy?
I think ultimately it comes down to the same issue. So what we're trying to do in those situations is store after they've been converted to electricity. So sun falls on a solar panel. We can generate electrons. We can use them right there and then as we need them. But if we want to use them when the sun goes out, we need to store them possibly in batteries, fuel cells, and other storage methods.
And I'm sure we'll discuss this in much more detail as things go along. But you've connected your research with the United Nations Sustainable Development Goals, haven't you? Can you tell us a bit more about that?
Certainly, yeah. So the primary goal that we aim to tackle is Sustainable Development Goal 7, which is about access to affordable and clean energy. However, I think whenever you deal with one of these things, you start to get into a nexus or a connection between other problems. So, whilst the primary target is around affordable, clean energy and access to it, we will also touch on things like climate action. We look at how we can develop technologies in a way that enable businesses to grow around an area, so that we can look at economic growth. And also we touch on things like water, sanitation and food, because, as I say, all of these problems are interconnected. So ultimately, if we consider the Sustainable Development Goals as a target that we can all set ourselves, impact on one quite often has impact across many of the others as well.
So it's not just Goal 7 in isolation?
Absolutely not, no. And I think that's an important thing to consider whenever people look at global challenges, is seeing that sort of bigger picture of what we're trying to work towards.
Now, I've heard that all of this started, or your research at least started, from watching paint dry.
Indeed, yeah. It is true. It made me quite the bore around my friends at one point, where I spent a large part of my life looking at paint drying. But that is absolutely true. Yeah. So early part of my career was as a chemist. I moved into, well, I actually did a year in industry as part of my chemistry degree, and that was quite interesting for me because in that case it was actually around sandpaper, even before paint. So watching how we develop resins for sandpaper. And I had that kind of moment where everything changed for me, where I realized that if that much thought goes into something that's so easy to overlook, what about everything else that's around us? So that then led me into a curiosity that took me to a doctoral program in materials engineering. And that was focused on increasing the throughput of a paint line for the local steel industry.
What's the throughput? Sorry.
So that's essentially one of the critical things for our industrial partners, is how much material that they can make in a given time. The more material that they can make, the more products that get out into the market. So a lot of my work has been around how we move from laboratory-based science into doing things at a big scale. And I think that's what excites me.
So tell us a little bit more about your doctoral work then. What did that involve doing on a day-to-day basis?
Okay, so essentially I was sponsored by BASF and Chorus, as they were then, which is now Tata Steel, so our local steelworks. And they'd invested in a production line that uses a particular wavelength of light, so near infrared, to dry paint. As you know, it always amuses me when I can talk for hours about drying paint, but I'll assure the listeners, I promise I won't do that right now. But essentially, we can use this to dry paint quicker, and understanding the fundamental science of how that works has enabled us to help them to produce more material, but it's also enabled us to look at other areas where that's important. So,
yeah, in what way?
So there's a twist in the tale of my doctoral work, which was that, as I say, ultimately we were looking at taking a process that takes 30 seconds in a traditional paint curing oven down to around about 7 seconds, so that we could do everything a lot quicker. But in understanding how that worked, looking at how the material absorbs light, what that does when it does absorb light, we were able to understand that we could apply the same sort of idea into solar energy. So now we can make solar cells a lot quicker than we could in the past. The big example that we discovered during my doctoral project with people who I still collaborate to this day, actually, on Sunrise, was that there was a 30-minute heating step that took one of the materials that we use to make solar cells up to 500 degrees Celsius. So quite a high temperature step. And that was to effectively to remove all of the bits of material that we didn't need there, and to create a kind of a network structure which we needed to capture light. Using the findings from the paint drying work, I still say that with a little chuckle, we were actually able to take that 30-minute step down to 13 seconds.
Wow.
And then that enables us to produce solar cells faster, cheaper, and with lower, I'm going to say, capital expenditure. But what I mean by that is the startup costs, if you wanted to enter into the solar market, drop substantially if you're able to do things quicker and with simpler equipment.
And when you say produce solar cells, I mean, what is the practical production of that like? How does it happen?
Okay, so the types of technologies that we work on in Swansea are a little bit different to the sorts of solar cells that most people will see out and about at the moment. You know, solar has taken off in a big way globally, so you see lots of silicon solar cells. These are produced in big sort of semiconductor processing factories. What we do is much closer to painting, so and coating effectively. So we would put down a layer of a liquid, and then we dry that liquid off, which enables us to create a sort of a porous, so almost a sort of a spongy sort of surface, which captures light. And then within that, we get a little bit of chemistry and physics that goes on to enable us to turn that light into electrons, which we can use for powering circuits or putting into a battery to store for later use.
Just in basic terms, what is that chemistry and physics that's happening there?
It's trying to think of a simple way of describing it. It's essentially the material that we put down is a semiconductor. It's a photocatalyst, and what it will do is effectively exhibits a photoelectric effect. So it absorbs photons that are incident on it, and that releases electrons from the structure of the material. They go off into a circuit. We have a few other chemical processes as the electrons re-enter. So we get some reduction and oxidation chemistry that goes on, so that we can recombine the electrons with the original material, and then that allows us to do the whole cycle again. So that's why it's renewable.
And these printed cells, this is obviously very different to what I think of when I hear solar cells, which is those things that people put on the roofs of their houses.
Absolutely, yeah. So these things, if we go back to another connection, I guess, between paint and solar cells, the kind of original vision for this was that the painted materials that I was making during my doctorate, their eventual application was typically on the roofing and cladding of industrial buildings. So, you go to a supermarket, they're usually metal-clad buildings which are pre-painted in a factory. Shotton Steelworks up in North Wales produces about 200 million square metres of pre-painted material. It tends to be double layered, so it ends up as being 100 million square metres of roofing and cladding material each year. And that is a vast amount. That's just in the UK. So our aim at that stage was we were effectively a corrosion and coatings group. We were looking to, produce this stuff at high quality with tartar, and then effectively guarantee it against corrosion or against something called photodegradation for up to 40 years. Now, photodegradation happens when paint absorbs light. Within the structure of the paint, we have these little semiconductors. We use them as pigments, so titanium dioxide being the key one. And when electrons get released from that, they damage the coating around it, so it all strips off. So the thought process was, well, actually, if we're producing 100 million square meters of this stuff, and we're spending most of our lives trying to stop sunlight from destroying it, can't we actually just use the sunlight in a more productive way? So that's the change in thought. So if you go to coating and printing processes, the eventual aim would be that you don't paint steel anymore, but you coat it entirely with solar photovoltaics. And then that means that the low-cost energy material is actually abundant around us, because all of the fabric of all buildings could eventually end up producing energy.
Wow. You've talked about patenting the NIR heating of solar cells. Now, is that related to what you're talking about here, or is that something separate again?
No, that's a similar process. So ultimately, the NIR is the near infrared wavelengths of light, and these are used to, as I say, to rapidly process the solar materials, but also can dry paint.
Now, I know just with my layman's hat on that one of the critiques of renewable energy is that it's often very expensive, and what you're doing sounds like it could potentially be expensive. Is it?
I think everything's expensive at first. I think that's one of the keys. But ultimately, the aim with this is to break down some of the barriers of getting into this kind of work. So I think an eventual aim for something like coatable solar cells would be that, particularly if we're looking at the global south, is to enable low-cost materials to be used. Now, there's a difficult economic argument to be made, because the cost of solar is coming down quite a lot as it is. And in fact, silicon is getting cheaper and cheaper. But there are still barriers in terms of the upfront costs to setting up a solar factory. And our aim is to effectively move around that. So we want to be able to create technologies which are easy to produce locally. And also, there becomes a little bit of a playoff. And this was quite difficult in the early days for a chemist and a materials scientist to begin to think about, because in a research environment, we tend to focus on things like efficiency. Everything we want to do is about making the most efficient solar cell. But actually, we have to think about if there are playoffs where we can use a low-cost, abundant material or a waste material. And some of my colleagues within the Sunrise Network are doing just that. So using waste materials as part of the kind of the ingredients of our solar cell. They may not be as efficient as using the very, very best materials, but it's dealing with a waste problem, and it's locally sourced. So I think at the moment, cost is still an issue, but the aim of this research is to bring down those costs, but also to enable more people to get active in the field.
I said wow a minute ago because I was genuinely surprised at this idea that you can coat buildings in a material that can generate and store energy. Now, what's the potential for this sort of technology? Because it sounds to me like it could be huge.
Absolutely, yeah. I think potential is massive. There are lots of things that we have to consider. So because when you hear a statement like that, one of the first things which will spring to anyone's mind is, well, why aren't we doing it now?
Yeah.
And I think that there are still some challenges, which is good for me as a researcher. One of the issues that we get is that we have to work on things like the lifetime to ensure that they last as long as we would need. Effectively, in the solar industry, we want to be able to guarantee things for 25 years. So there are still some challenges around that. But ultimately, I can see that there are ways of taking slow steps towards doing this. So on the Swansea University campus, for example, on the Bay campus, we have two example buildings. We have the active classroom and the active office. Now, these are buildings that are going to take the sort of the baby steps towards that future. So on those buildings, we have a roof material from a company called BIPV Co Limited, and BIPV was a spin out of Swansea University with Tata originally. And what this does is it produces a steel sheet which has a very thin film solar bonded onto it, and that means that the look of the building is very different. It just looks like a steel roof. But it's not quite where we want to be just yet. We still need to develop the coating technologies, but that will help to get the market to understand the potential. The next thing that we do, and there's a lot of this within the Sunrise project, is to look at the existing silicon market and then develop the sort of printable techniques. So one of our collaborators, Professor Henry Snaith in Oxford, developed a technology called the perovskite solar cell. And his work at the moment is focused on what we call tandem cells. So tandem cells are where we coat one type of photovoltaic technology on top of another one so that we can boost the efficiency of both of them. This works alongside silicon, and the eventual sort of aim would be to almost bring the two together. So if you could have those flexible coatings that we're printing on top of silicon and just going directly onto a roof material, that would be the perfect solution. And I think that when we're at the stage where that is viable and cost effective and can be guaranteed for long enough in exterior exposure, then I think we'll see a massive uptake. And I think at that point, there is very little limit to how far you would go. I think it would be crazy to put up a new building without having those sorts of materials on them.
You've mentioned the Sunrise project a few times. Do you want to just give us a bit of context to that and a bit of background information? I mean, when did it begin, for example?
Okay, yeah. So the Sunrise project is it's 2 years old now, and this was a bringing together of a lot of interesting groups who were already beginning to work together around solar energy. So we have a specific innovation and knowledge centre in Swansea. So that's the kind of project that developed the active classroom and the active office. So that's focused on essentially the things that we've talked about just now, where we look at how we can take things from a lab into a sort of a production and then demonstrate on a building. But we do that in a UK context. At the same time, so that's been running since about 2010, I should say. Around about the same time in 2010, there was a consortia formed of Indian academic partners and UK academic partners, and they were focused on essentially the science of solar cells. And what Sunrise did 2 years ago, so back in 2017, was to bring those two things together in a more meaningful way. So this was taking 5 UK university partners, 7 Indian university partners, and building on their science so that we can move forward to demonstrating buildings in India. And it's quite a wide-ranging project because we're doing everything from the fundamental photochemistry and the fundamental photophysics to develop new cells through to how we can actually make those in a production environment, through to what that means for a building. So it's a large project with lots of different skill sets involved in it.
Going back to the details of the research then, you've talked about microgrids. Well, firstly, can you explain what they are? And you've also talked about energy hubs. I assume the two are related.
Yeah, they're kind of two sides of the same coin in a sense. But I think that this is really about contextualizing energy, particularly in places like India. So, I mentioned earlier the vast number of people who don't have access to reliable 24/7 power in India. There are various approaches that you could take to try and connect them. The traditional approach, of course, would be a fossil fuel burning power generation center, and then a national grid. So a little bit like what we've got here, where everybody's sort of grid connected. That would be one approach. Now, there is an ambition, and again, I love working in India because the Indian government are so ambitious on these things. And there's a real passion for solar in India at the moment. But one approach to doing the interconnection of villages and communities would be to essentially just replace the big power generator, the big fossil fuel burning Mount Doom style factory with a solar farm. And that's good, it's clean energy, but then you're still reliant on being connected up to a massive national grid. And there are challenges with transmitting power that far, particularly over a range of climates and geographies as you get across India. So the micro hub, the energy hub or the microgrid, the idea there is that you generate locally and you store locally and then you use locally, and you may want to interconnect those things. So it's essentially, instead of having a massive national grid, we could have a village which looks after its own energy needs. So you have everything on site, from your generation through to your storage and your distribution to local homes, local community buildings, or anything else that you need power for. And personally, I think that makes quite a lot of sense in the context of a place like India, because of the challenges of running a grid. However, you can still, so that's why we call them microgrids. It's like a miniature grid based around a small community. We could do it on a university campus, for example, and that could be its own little microgrid.
Don't these microgrids have to still be connected then to a backup larger generator, even a Mount Doom style, factory, like you say, just in case they do fail or go offline?
They can, and there are ways of doing that. So one thing that you could do is you could interconnect all of the microgrids. Now, that sounds complicated.
Isn't that just the grid?
That is just the grid, but there is a slight difference in that all that you're doing there is that you are, effectively exporting any excess that you've got, or importing, and you're doing that at sort of much lower levels. So the infrastructure doesn't have to be as hefty, I guess, as you would for a national grid. But there are other options as well, and you can have backup locally. So within the Sunrise project, we do actually have work packages based around things like biomass conversion. Now, again, that's effectively using waste. Could be agricultural waste, could be municipal waste, so rubbish and bits and pieces. Could actually be human waste, but that's another story. And we can use that as the fuel, effectively, that powers a backup generator. And then that can ensure some level of reliability. in fact, in many ways, probably more reliable in the future than a fossil fuels reliance, because you do get energy security and issues around fossil fuels. So if you're not a country which produces many fossil fuels, you're reliant on import. And what happens if something stops the import? So actually, if you can use your own waste as your backup, it could potentially be more reliable.
Can biomass mean things like wood pellets as well, or is that something different?
It can mean wood pellets, and quite often does. We have to be sometimes a little bit careful with wood pellets in certain contexts, because one thing that we certainly don't want to encourage is any deforestation for power. But where there's excess wood, or as I say, wood pellets made out of sawdust waste, that kind of stuff, then there's certainly application there.
What would you say to people who might be a little bit critical of this and say, these microgrids, often based on solar energy, are going to be, for now at least, relatively expensive, relatively unreliable, and perhaps these people deserve just to have their Mount Doom fossil-fueled power station giving them reliable, cheap energy?
I think we have to be fair, and we have to acknowledge some of those concerns. However, I think that the relative expense in the early days will be mitigated in future, because lots of these things are based on economies of scale. So, as I say, solar is pretty much at the moment, just using silicon is probably one of the cheapest forms of energy at the moment, believe it or not. We have to project into the future what might happen with fossil fuel prices. So there will become a tipping point. But one thing which we do have to be absolutely clear on is that nothing that we would do in a village would ever be too experimental. Because we're dealing with human lives at that point, then absolutely everything that goes out there has to be reliable. But the biggest counter to anyone who would argue that the continuation of fossil fuels is, a fairer way of doing things, is that actually in the long run, it's people's health will deteriorate and is deteriorating. I can give a good example actually of last couple of times that I've been over in India. So I'm an iPhone user, and when I look at the front of my iPhone, it gives me the day's weather wherever I am. And, being from the UK, pretty used to seeing cloudy.
Being from Swansea in particular.
Yeah, definitely. Yeah, cloudy, rainy. Very occasionally we get sunny spells. But the last time I was in Mumbai, my phone said that the weather conditions were smoke. And the last time I was in New Delhi, the weather conditions were unhealthy.
And by smoke, they mean smog.
They do, yeah. Yeah, so, that was quite, I actually screenshotted it because I thought that's something that you don't see every day. And it reminds us of the importance, actually, of moving away from fossil fuels.
Talking of Mumbai, how often do you get to go to India or other countries indeed?
India, usually once or twice a year. So we would tend to have an all-partner meeting over there. And as I say, I do travel quite a lot with work as well. So I have some projects in South Africa. The last few years, probably been to the States at least once a year. So yeah, it's an interesting one. You do travel a lot with this kind of work.
And where's your favourite place to travel to?
No, that's a real tough question, actually. Everywhere's so different for so many reasons. But I do absolutely love India.
You must have a lot of stories, or from your experiences of India in particular.
Yeah, I mean, we've had some good experiences in India. I mean, it's a fascinating country. One thing which I kind of struggled with initially, of course, was there is quite a big gap between the rich and the poor, but it's not necessarily a geographical gap. So effectively, you can walk out of one building into a street and see absolute polar opposites in terms of people's livelihoods. So yeah, it's a fascinating country. But one of the things which I think is quite amazing with India, and a few of my colleagues, we now have a little bit of a motto, which is, and I think we can all apply this back home, which is have a plan but be flexible. And this comes down to the kind of organized chaos that you see everywhere, and not least when traveling, particularly in the big cities. So if we take Mumbai as an example, the traffic system there is unbelievable when you're used to UK roads and UK gridlock actually as well. Because you see these lanes, which, to me, they look like there's only supposed to be 3 cars wide, yet somehow you can definitely fit 6 cars through it, and you can squeeze a two-wheeler, so a motorbike through with a whole family on it. But amazingly, it works, and we've reflected on this quite a lot. And I think one of the things which I've realised is that actually, if you stuck a load of traffic lights and calming measures and things in, it wouldn't work anymore. And that's something that we have to bear in mind with the context as we look around the world, is that things work differently, but actually on the whole, they quite often work.
What about the optics here of somebody researching renewable energy, jumping on an aeroplane and going all over the world quite a lot for meetings that could be conducted remotely? I
was looking forward to that one, because it is actually something which I do grapple with quite a lot. And it is a very, very important point. So, my personal carbon footprint is absolutely massive because of the amount of travel that I do. So it is genuinely something which I think about a lot at night. I think, how can we do these things? So I think that there's an interesting playoff in my mind on this stuff, about the fact that sometimes when you're working in these kinds of environments, you really do need the context. We try and do as many meetings as we can virtually. Things like Zoom and WhatsApp have completely changed how we all work. And, the world is a much, much smaller place because of those things. So that certainly limits a lot of our travel. However, there is really no substitute for visiting a village and understanding how people live in a village in India. And the thing which I find really important is that I think that I've changed personally because of the things that I've seen on the ground. Now, that then throws me into this sort of really difficult dilemma, because actually when I talk to lots of people who really do care about the environment and want to make the world a cleaner place, most of them are quite well travelled. So there is this sort of strange, almost like catch-22. I think the global citizen is probably the one most likely to spot the issues, but is also a major contributor. What I do try and do now is, if I am traveling, I would never just travel for a quick meeting. If I'm going to India, then the key is to pack in as much as you possibly can while you're there, so that you can mitigate against future travel, and you can achieve more for the carbon that you've expended getting there.
The research that you've talked about has been applied, or can be applied, to water and sanitation issues as well, can't it? So can you tell us a bit about that?
Yeah, sure. So I've worked and still do work quite a bit with the Bill and Melinda Gates Foundation around water, sanitation and hygiene. And this is, again, it's a fascinating topic and quite a terrifying one when you get into the details of the number of people globally who don't have appropriate access to, toilets, effectively, and the knock-on effects of that. So if you take the sanitation issue, more children globally die each year from issues with diarrhea and poor sanitation than things like measles, malaria, all of those things combined. So it's a huge issue. And in terms of the technologies, some real challenges, because you're quite often in a water constrained area. And if you look at the UK infrastructure, we're blessed here by having a sewage system, Victorian sewage system, I add, which is massively inefficient, and we use gallons and gallons of water to flush away our own human waste. But actually, that did the introduction of things like the sewage system that we've got did correspond to a massive jump in life expectancy in the UK. And there's no reason that we shouldn't be doing that overseas. So the technology link actually starts back with drying paint.
Yes.
Everything goes back to drying paint. So it's not such a tedious topic after all.
Well, I've read it relates to this lovely phrase, which is not drying paint, which is fecal sludge management.
Indeed, yes. So fecal sludge management. It's I'm for your listeners, I'm not going to say what that really means, but it's drying something else. Certainly, anyone who's listening at breakfast time or just before lunch certainly won't want me to go into any detail.
We probably get the gist.
Yeah. So effectively, this all spans out of a conversation, and again, another one where I was traveling. But essentially, what we realize is that if you look at fecal sludge, it can be up to 90% water. Now that gives us a lot of issues. You're in a water-constrained area. Human waste has got sort of 90% water in it. We need to remove the water and essentially kill all of the bugs that are in the sludge. And we need to do that efficiently so that we can go on to use the dried sludge for useful things. Now, by useful things, it's actually quite amazing what you can get out of human waste. There are projects within the Gates Foundation which turn sort of dried fecal sludge into a power source. So effectively, you can do something like a pyrolysis step or effectively other kinds of heating or combustion, and you can end up with power. You can end up with a biochar or a soil conditioner, which can help people grow more crop and better food. And if you've removed that sort of 90% moisture in a sensible way, you can actually recover water, clean it up, and use it as drinking water. Now, my initial link to that was around making the drying step more efficient. But in reality, there's a lot that you can do if you've got excess energy from an active building. So the sorts of things that we think about now are, could we use a building to drive sanitation? So you go into a community, the aim is initially to provide power, but can you deal with a waste issue that stops people coming into contact with pathogens or bugs that are going to make them sick? And in doing so, can you increase the productivity of agricultural land while simultaneously helping with the water burden? So, yeah, it was quite an interesting world when I started to think more about our own waste. One of the big areas that people talk about at the moment is the circular economy, and I'm not sure if people will come across that phrase, but if they haven't, they certainly will soon. This is about moving to resource efficiency in everything that we produce. So when we produce something, we should have the end of its life in our sights and think about how we can reuse it and take steps to ensure that nothing effectively ends up in landfill. And I think that actually the sanitation projects are the ultimate circular economy, because we should be applying it to our own body. So everything that we eat, we should think about what happens to the waste stream and whether we can get some value out of that as well.
Mentioning the Gates Foundation there, obviously that's a collaboration with a huge organisation. Sunrise is for an academic collaboration, a very large scale one as well. But what about the collaborations that you've had with small organizations? I read something about the T-shirt manufacturers in Mexico, for example.
Yeah. So this is, this is some of my colleagues within the Swansea part of Sunrise. So Professor Tristan Watson and Dr. Adrian Walters and their team. We've been talking for a little while about how we use screen printing. So if you go into the labs that we have in Swansea, we have quite a lot of screen printers of varying size and complexity. But ultimately, the concept of screen printing is relatively simple. And I think effectively there was an area of thought around, well, we're trying to show that that we can develop this low cost way of producing solar cells. It started almost as a bit of outreach, we used to go into sort of school groups and show them that you could make a solar cell in a very simple way. But then a collaboration was forming around the science of solar cells with University in Mexico. My colleagues have been out there a couple of times now and run workshops, both with school children who, they demonstrate that these materials are printable. And again, collaborative research in the university. But then the next step was to really try and prove the concept. Can you go into a commercial T-shirt manufacturer and produce solar cells? And that's the work that they've been doing over the last few years, and it turns out that you can. So again, just screen printing. Basically, all that you need to do is have a pattern in a mesh, and you effectively you drive a printing ink through the mesh so that it leaves an image of that mesh behind. In our case, we would obviously be looking at the most efficient circuits, but it does open up all sorts of weird possibilities as well, where we have in the past produced patterned solar cells, which are a little bit more visually attractive.
And is it important to work with different kinds of organizations in terms of size and scale? These smaller organizations, you say it's almost like an outreach thing, isn't it?
Yeah, I think it is. And, one of the really important parts of something like Sunrise is, how do we get this from being an academic consortium with some good ideas and a few demonstration projects into something which is widespread? And I think that that's where working with organizations of different size becomes really important. So, certainly access into the Tata Group within India is big in terms of opening doors. We can certainly have an impact there by a shared voice of such a big organization. But in reality, on the ground, we then, I think in a country particularly as vast as India, we would probably be looking to the sort of small to medium enterprises locally to produce some stuff themselves. So experience of working, and that's where the T-shirt idea is really nice. If you can take a relatively small organization who make T-shirts and then upskill and uplift their ability to produce a new product, then it's right at the heart of the kinds of communities which will be using the technology. And that's a real key for that kind of widespread message. So if you do it with one, you then need to disseminate across. And I think that, again, we talked about carbon footprint of travel earlier. That's why a lot of this needs to be locally sourced and done near the point of use.
Sticking with that, and you have touched on this a couple of times, but you've spoken about the need for responsible consumption and production. And as so often, this is actually a case of science and politics colliding, isn't it?
Yeah, absolutely. Yeah. No, I think that that's a very, very important point. And, we have to think about that with the materials we use. We certainly don't want to end up in an issue where all of these things are reliant on a particular material that creates another issue further down the line. So, There's lots of discussion around this with battery materials, for example. If we were to use a material which is unsafe or difficult to get hold of, or increasingly you can get it from an area where there's conflict, so we call them conflict materials, that for us is a big red flag, which we would try and engineer ways of not using that material. But also thinking about, and this is where again a business element comes in, what do we do to recover our materials at the end of life, so that rather than constantly mining things out of the ground, we can actually look at what we would call urban mining, I guess, where we look at the resources that we've used in the past and how we can employ them in future materials.
And I know that you think that education and gender inequalities are very important in this whole story as well.
Most definitely, yeah. So I think education and actually, and equalities across the board wherever there are minorities, but gender is a huge issue globally, and is compounded in certain cultures and groups. I think that what we would hope to do is by producing sorts of projects that we do overseas, is to develop an infrastructure where we can aid with education across the board as well. Naturally, if it comes to me, I'm going to talk about science and engineering, but actually, there's lots of other things that we need to bring people up to. So things like access to justice and understanding the legal system, those are all really important. But as I say, quite often it is young women that get left out, and that's for a variety of reasons. It's a very big topic, for example, within the world of sanitation, is that just by improving access to sanitation, we effectively can see more people participating in education for longer. The longer that they participate in education, the better their potential outlook at the end. So all of these things combine, and as I say, an intervention in one does tend to have knock-on effects in others as well.
In terms of the technology and of the future of energy, are you optimistic? Because a cynic might say that in India, for example, certain companies, the government even, are very good at making the right noises and saying the right things. But actually, my understanding about India, for example, would be that they are still rapidly opening coal-fired power stations.
I am optimistic, yeah, and I think there are issues, and I think the issues are that the speed of growth is phenomenal, and at the moment, we have a limited toolkit of growth, and I think that this is where sustainable development goals generally come in. And these are important across the board, both overseas and at home. I think it is a little bit of a race. We need to get it. We have a constant time pressure on us because we need to be able to develop these technologies and deploy them quickly enough that we have a realistic chance of deferring some of those large infrastructure projects. But as I say, we will always have the fine balance where you don't want to hold back a developing nation either from their ultimate goal of development. So I think I am optimistic, and I think the pressure is on all of us actually to develop not just the technologies, but the community involvement piece and the business models and everything that goes with it to enable deployment at the scale that's needed in the time that it's needed.
People might be listening to you, particularly young people, and thinking that not only is the science that you're engaged with really interesting, but it is also, doing good, or you're trying to do good. So if people wanted to get into your line of work, how would you encourage them to do so?
Well, I have, my own pathway, which was, again, for me personally, I studied chemistry. and went on to do a doctorate in materials science. But I think ultimately anyone who's working in science and engineering at the moment will have, or is increasingly likely to have, sustainable development goals on their mind. So those sorts of careers are really likely to drive you in that direction. And it could be the really unsurprising thing. The really surprising areas as well. So you quite often see a lot of people wearing pin badges at the moment, which have the circular pin badges with lots of little colours on them. And if you don't know what they are, you probably overlook them. But they're actually they represent the Sustainable Development Goals, and you see those being worn by scientists and engineers from everywhere. So large construction companies, automotive manufacturers, everyone has these goals on their mind at the moment. So if people want to do good, there's a really strong case that getting into science and engineering now gives you an opportunity to be there at the right time.
Ian, thank you very much. If you want to find out more about Ian's research, you can visit his staff profile at Swansea University's College of Science webpage, or visit www.sunrisenetwork.org, or visit www.m for mother, the number 2a, so that's one word, m2a.wales. To find out more about this podcast and Swansea University's research, visit swansea.ac.uk/research. That's all from us today. Thanks for listening, and thank you again to our guest, Dr. Ian Mabbett. If you've enjoyed this episode, please subscribe, rate, and review. I'm Sam Blaxland, and that was Exploring Global Problems from Swansea University.